I have the chance to introduce you to a Python package that we actually developed and which is open source. And it incorporates at its very core a case generator to create n-dimensional or multivariate simulation cases. So whenever you are to really explore your operational design domain, your ODD, to test your model, then farn can support you. And I'm really standing here not alone, rather on behalf of also two further colleagues. So the three of us are kind of behind this. The perspective we had on model testing originates a bit from the perspective on, say, looking at model assurance. So, I mean, we at DNV, we are a trust provider at our very heart. So, and this model lifecycle you will find in the recommended practice on assurance of simulation models, and a part of it is on modeling, which we will concentrate on today. And we thought, well, what comprises modeling and creating a good model? That is obviously that you would need to code and you would want to code. That's why we're here. But also that you need to build simulation cases that you then actually can test your code against and then executing this code. So we are likely not able to help you on the coding itself, and maybe we don't want to, because I mean that's really the design work that you want to do as potentially being model providers. But maybe we can help you in running and in building cases. And running cases is obviously OSP that provides the tools and the architecture. And what farn addresses is this challenge of creating multiple simulation cases once you want to explore an n-dimensional operational design domain. So that's say the ambition behind farn. So what is it? Farn is a case generator, as I said, and basically if you ever encountered yourself in a situation like this, and maybe you didn't, but it was only me, then once you start testing your model and running through different scenarios, then you start varying parameters and that stuff, and you quickly end up with something like this. And what farn basically does, it turns it into something structured and nice, and helps you to automate that procedure, also to automate and repeat your tests to properly traverse your operational design domain. The core functions are to sample an n-dimensional space. We have currently 3 sampling algorithms implemented, which is fixed, so you would only give certain distinct values a variable can take, then linearly spaced and uniform Latin hypercube sampling, and the LHS then gives you the ability to vary multiple degrees of freedom, multiple variables at a time, which is quite a good stuff. So, and then once you sampled your ODD, then farn helps you to generate a corresponding folder structure. So all this is to ease testing a model locally, which is, Thomas, as I said, I fully agree, right? Start doing, creating FMUs locally. That's what you're supposed to do. But once you say start sharing access to your model or collaborating with others or going into co-simulation, you probably want to be sure that your model is good, working properly, because that's something that you expose also your very own work to the world then, or to your customer. So testing that is great. And if you're working locally on your on-premise or on your machines, then having a folder system is just fit for purpose. And finally, it's about executing user-defined command sets. That is really shell commands, but farn takes care of executing those commands that you define in each and every case folder. So for the automation stuff, that is of help. So that's about setting the scene. Farn is Python. It's a package. It is registered on the Python package and index at PyP. So you can pip install it. We'll see this. There is a documentation out there on farn hosted on GitHub pages, and there is also a repository called farn demo, and this is what we will look at today and briefly run you through. So first, installing farn. If you're familiar with Python, I choose the Visual Studio Code, VS Code, as editor and as development environment here. And you would say, assuming you have cloned this farn demo repository, you have it on your local disk. In my example, it's just on C drive dev farn demo. So right. So let's put this terminal on top. So then what you would typically do first as you work with Python is to create a virtual environment, because then you have all your dependencies and installed all your dependencies project specific. So you activate that environment and then you're ready to install farn. So you would pip install farn, and then all the dependencies farn needs get installed. And what you can see here is farn had been installed, but also two more packages I would like to draw your attention to. That is dict.io. That's one of the foundation packages that allows us to write to and read from dictionary-like files. And farn uses text-based configuration files. It works with JSON. We started out with a more proprietary or native format, which say uses less of double quotes. JSON is very double quote heavy, and we had we supported in say a cleaner or less quote heavy format that comes from OpenFOAM, so that is also supported. But JSON works as well. And then there is OSPX, and OSPX is a package that deals with OSP configuration files. So all those three you get if you install farn, and if you call help on the command line for farn, you get some help. What we will concentrate today on is three. It is sample, which is a command to sample your design space as configured in a configuration file. We'll see this. Then generate the folder structure and execute certain command sets in all case folders. Starting with a demo. What is the demo task or the challenge? Imagine it's very, very simple. We just have some inputs called x1, x2 here, or mean and subtrahend, and we calculate difference. This difference is used actually as a divisor for a quotient. So we have a third variable, third input called the dividend, and then dividend and divisor say creates the quotient, which is our output also. And basically that's the system boundary or model boundary. That's a very, very simple model, just some mathematics in between. Now, what you would want to do is you want to vary those three input variables in certain ranges. Let's say x1, x2 from -10 to +10, and x3 from -20 to 20. That's all. So three-dimensional design space and some variation of those inputs. The only thing that you need to observe is that the divisor must not be 0, because otherwise you will divide by 0, and that's something that you want to avoid. So the task for farn sampling is basically vary x1, x2, x3 in these ranges, but exclude cases where minuend minus subtrahend equals 0. Simple task. So if we just say switch into the farn, that is then the farn demo in this. There's a subfolder called farn, and if we look into that, you will find something like called a farn dict, and I will repeatedly talk about it, something like called a dict, config dict, and that is basically this text file that contains all the dictionary-like configuration information. You also see just below there farn dict.json. So as I said, you can do the very same also with the JSON form. If you look into that, then you'll have say two sections. First one is environment. It's not so important, but it basically helps you to set some environment variables on your local machine. Only one is important here, setting a directory you would use as a template, and this is something that you can reference then later on. But more important is layers. Layers is what really defines your sampling. And you can have one layer, you can have multiple layers. Layers gives you a semantic, say, artifact to group variables. So we only have 3 variables that we varied today. It's just x1, x2, x3. Very simple. We only define one layer that uses LHS sampling. But we could also define 3 layers for each variable, 1 layer with some, I don't know, some linear spaced sampling or something. So it's just for you to know you can define multiple layers right after another, and you can name them however you want. LHS var is just an arbitrary name we gave this layer. Inside a layer, you have say certain sections on with properties that correspond to that layer. First is sampling. So let's look into that. We say, okay, sampling type is going to be uniform LHS. Then we have names, and we call it just names because what you use those things for is totally up to you. Farn is not interested in whether you do simulations or something else, right? You vary something, and we name it minuend, subtrahend, dividend as those 3 input variables. And you define the ranges; they should be varied. And we say, okay, number of samples for the LHS is 20. So from Latin hypercube sampling in this 3-dimensional space, the sampling should provide us 20. Select randomly 20 samples. But we also say include bounding box true. What does it mean? It means that all bounding box, all the corner cases should be included as well. 3 dimensions, 2 to the power of 3, 8. So this means 8 cases, bounded box cases come on top. So the total number, theoretical number for us exploring this ODD is 28 samples in this 3-dimensional space, 20 plus 8 corner cases. Next is a condition. This allows you to express some filter conditions. In our case here, whenever you see that minuend minus subtrahend equals 0, please exclude them. And then there is commands, and that corresponds to this executing certain command sets in all those case folders. Again, arbitrary names, you can name them as whatever you want. We clustered it into prepare, run, and post for post-processing. We'll look into that once we get there. Let's start with the sampling. If you call farn dict, and that's this configuration dict, right? And then --sample, it's gonna sample this file, and it says, okay, I successfully listed 24 valid cases. 4 invalid cases were excluded. They are not really invalid. It's those cases where you define this condition and you said, okay, whenever minuend minus subtrahend is 0, please exclude them. This is why it says 4 were excluded. So from this 28, 4 were excluded, 24 were valid. And we now have a new file that's called sampled farn dict. So looking into sampled farn dict, there's a new section here in this layer, and that's being done for each and every layer. We only have 1 layer here, but for this layer, we now have a section called samples. Looking into, we have names for the cases that relate to this layer. And they are just taking this base name of the layer you provided and then appending an index. And then you have the individual samples of those 3 variables that you do vary. This is down below the screen. But basically those tuples that in the vertical that belong to each other, this is one, forms individual samples in that 3-dimensional space. The dividend one is below here, not to be seen. But these are then samples actually for each and every case. And the first 2 are ones that will be excluded when we generate the case folder, because those are the ones where this exclude filter triggers. Minuend subtrahend has same values in those 2, so the difference will be 0 and they fall out. So next step is we will create the case folders, and you will see the first case folder being created is LHS var 02. 0001 will will be omitted. So farn generate. And now we take the sample to farn dig as an input, not any longer the very original one. I say dash generate, and it generates the case folder structure for us. And if you look to the, okay, it says, okay, I created 24 paramdig, again, text file, files in the 24 case folders. The paramdig files, this is where the individual case-specific combination of values of those say parameters that we do vary is being persisted. So in each and every case folder, farn will drop a paramdig file. In this paramdig file, you will find those the 3 values. If we look in this here, we have cases. We have this exemplary first case folder that we look into. There's a paramdig file. If we look into this, you will see that is this case-specific combination of values that applies for this specific case. And in each and every case folder, this paramdig will look different. So this is what makes it case-specific. There's also some more information, but that is really meta information for kind of debugging, so you know where it comes from and why it is those values. But that's not decisive. Those 3 variables up there, that's your say persistent configuration. And then you can execute commands, and that's arbitrary. That's shell commands. You can do whatever you want. What we do, and let's look into the first group here, is prepare, is saying, okay, we want to first copy something from a template directory. That is what we defined in this environment section. We said, well, there's a template, a directory called template. You should use that as a template directory. From there is a case dig, also again a configuration file. Please take this and place it in your current working directory. That's the dot in the end. So in current working directory means then each and every case folder. So what farn will do, it will jump into each and every case folder and then execute those shell commands right there. So you copy this into the case folder, then you do some, oh, that's the template dig there. So then you do some parsing of that case dig, and we will see that is exactly what turns a case agnostic configuration file into a case specific configuration file. And then we build an OSP case out of it. So observe our case folder here, the LHS var02, when we execute the prepare command set. Again, we take the sample farn dig and call execute, and then execute prepare. This is the name we have given to that set of commands. And it will say, okay, I execute these 3 shell commands in each and every case folder. Successfully executed command set prepare in 24 case folders. And if you see now, there are quite some new files. First, it's the case dig. That is exactly what we told him. Say, take the case dig from this template directory, copy it into the case folder. And then there's also parsed case dig. And this is, let's look at this. That's a bit what it does. So in the case dig, and please, that is an information that is basically coding or describing your system structure. That translates then into an OSP system structure XML, but it can be anything, whatever you need in your domain. You here have a start variable, but it is not given as an explicit literal, but you are referencing something. You are referencing a name with that syntax of this dollar. So you just say dollar minuend, and up there you have an include directive, and this include directive points to say include paramdig. So this file is case agnostic. That is something that you do once. You put it in the template folder, it will be copied into all case folders, but it stays there, case agnostic. But it tells farn, look into paramdig. Find what is called minuend. Take that value, replace it. And then this is what is being created. That is then called parsed case dig. 3, nothing else than this case agnostic configuration file turned into a case specific configuration. So you salted that with case specific values for those parameters that you vary. That is parsing. Now looking at the next command set, which is actually running simulations. In our case, we execute a COSIM OSP simulation, and we run the OSP system structure XML. This is a file that is in every case folder. It is also be turned to a case specific. So this initial value stuff is looks different in each and every case folder. So for this OSP structure, system structure XML, and we execute it in all folders. Again, look at our case folder. What happens if we now execute this command set? Boom. And you see already, these are the typical CSV files that COSIM generates. Here we go. Successfully executed command set run, which you named run, could be named anything else, in 24 case folders. And we can see here these CSV files. That's exactly those CSV files that OSP COSIM or COSIM spits out. And then very finally, we have one more, say, command set defined that is for post-processing. There is a small, say, tool called Watch COSIM. It is not, honestly, it's not so mature yet, but what it does, it summarizes a bit of the results and does some basic plotting. But that, again, that can be anything that you can execute on your machine. So let's execute that command set and observe our case folder once again. What happens? Okay, successfully. But we now have a new folder in there called results. That is something that Watch COSIM does. But again, you can execute whatever you like as scripts, and it puts all those CSV files into there. It also creates a summarizing dict which contains some statistics for each and every variable, an output variable of those models. So what was the latest value and not last value, because you can actually call Watch COSIM even during a long running simulation. So then it will spit out the latest value it saw. It will also create some very basic matplotlib say PDF with your outputs. As this example that we use mathematically is rather simple, all of those are constants. So not really interesting, but if you have more advanced simulation that you run, this can give you at least a very, very quick glimpse on what the output was. And this is being placed then in each and every case folder. So, right, collecting this, dumping it into something more more sophisticated is not yet implemented, but that's scratch code. But summary. So what farn can help you to sample an n-dimensional design space, that is this, say, argument or option -- sample. It generates, it executes arbitrary command sets. It's open source, it's Python, it's installable with pip. It's open for contribution as well. Very happy to have you as contributors also. It includes a command line interface that this is what we saw, but also you can do the very same also through the API by including, say, or importing the package and its namespaces in your Python software. Documentation is linked here. The code is at dnv-open source. There's also this demo, that is the farn-demo repository that you can download and then play around with, the very same as we saw now, and which I guided you through. That's it for me today. Thank you, and open for questions, of course.
Excellent. Thomas has a question. Yeah, because we're still recording the session. So if we want audio from your question, you need to wait for the microphone, please.
Oh, hello. Thank you for the interesting presentation. Always like to see automation and the generation. I especially like that you go through an immediate format that is not specific to any kind of tool. I'm just thinking, in your case, you argued for filtering out cases where you have a divide by 0, which makes sense from a mathematical standpoint, because that's not something you would do. But in some cases, it actually makes sense to test those things, because you want to see that the result is actually undefined when you do that. Can you handle those cases through farn, or how would farn respond to an application that misbehaves when it crashes?
Yeah, you're completely right. Of course, when testing a model, we might and we should possibly be interested in exactly those cases which potentially crash or are critical. How the FMU behaves in that case, I don't know. Right? So that's something that we would simply need to observe. Maybe there is an expected behavior for certain cases. That is something that those aspects we deal with in the model assurance workshops. So are there specific scenarios that you know are invalid, but what is what we expect as a behavior of that FMU in that case? Maybe it should signal something, an invalidation flag or whatever. So that could be specified and then hence also dedicated to be tested. I had a second thought on handling. Yeah, exactly. Identifying those cases. I mean, here it was a priori knowledge, right? Very simple. Okay, we know we can't divide by 0, so okay, let's exclude it. But in real life, maybe we do not know in advance, and even we would deal with black box models probably also. So it is about finding those critical areas. It's about finding those spots. And that is actually what we are currently working on, which is also part of the, say, verification work then in this assurance life cycle. And that is a lot about, say, having some smart sampling, right? Where you start with a reasonably small set of initial samples in your operational design domain, and then search for new samples depending on your outcome. So that is where Gaussian processing comes in, right? And creating surrogate models, machine learned models, and then looking, okay, where's my uncertainty in that space? Still high, so I need a new certain sample which I want to simulate to gain some new information, and then dynamically finding out new samples, always on the search for critical spots. Because everything that is not critical and low uncertainty, we could consider, okay, boring stuff, don't waste additional simulations there, but as quick as possible finding the critical areas in that n-dimensional space, and then also balancing in between exploration and exploitation. Because say you first start to explore, then you find something, and then you want to exploit that. But you want to come back at a certain stage also back to exploring, because it might not be the only critical area you want to look into. So right, and that is then more that comes on top. This is really, say, the basic stuff, the deterministic stuff of sampling. Smartness comes on top. However, can use the instruments and the tool set of farn, and then interacting via the API using farn to dynamically do resampling and create new samples and so on. And this is what we do. Yeah.
Yeah, I used the Barnsley fractal as a logo, which I found very good. Is there like some recursiveness built into farn, or?
Sorry,
Well, I used the fractal as an icon.
did I?
Yeah, the farn.
Oh, yeah. The fractal. That's the Barnsley fractal.
That's what I mean. Yeah. So
Yes,
is farn also meant to like,
yes,
be recursive and like
yes,
say...
it is recursive. And as you have those layers, we only had defined one layer where we said, okay, in this layer we do some Latin hypercube sampling combining 3 variables. Fine, one layer. But you could have, say, 10 variables, and then 3 of them you group into a Latin hypercube sampling, and then another 2 you vary with linear spacing and whatever. And then you have maybe some distinct values for a certain parameter, just one on-off stuff, right? And you say, okay, additional semantic layer for that parameter, and we vary it for in between the fixed states it can take, 0 and 1. And then the resulting samples out of each layer are being permutated by farn and translate into a nested case folder structure on your disk, right? So this, in our case, the cases folder contained only one level. But if you have multiple semantic layers where you define your sampling, then you will have multiple nest levels in there, and that is basically this farn analogy from the Barnsley fractal. And again, that's Frank.
Yeah. For the fractal. Yeah.
So
Great. Another question? Yeah.
I had one, but I think you've already answered it in your have Latin hypercube sampling already right now. How easy or difficult add probability sampling?
that's what we're currently exploring. So as soon as you turn information that you created with simulations, so once you simulated a certain set of samples, then you have information on at the sampling points. If you turn that into a model that you learn, into surrogate model, and you use a probabilistic model like a Gaussian processing regression model, then you get also a probabilistic distribution. And this then in turn you can use to do resampling. But they say the process of decision taking where to put the next sample, this is out of the current scope, and it's also out of the current, say, responsibility of farn. Farn does it for you if you know what you want, but the smartness of and deciding where to sample next is a certain responsibility that I would a bit of isolate from farn. It's a different role you would model.
There was one more question in the back. If we maybe last one, have to be mindful of the time as well.
You might have answered this, but
this question, but it's kind of related. You use it for optimization of just if you're searching through the end space, quite easy to just. Does it already have the capabilities, or do you have it planned in?
Here, it does not have optimization capability, but that is really only down to your objective function that you have. I mean, it helps you to batch execute all those simulations at whatever points in your space you want to be simulated. Then you have the results, and the optimization would then say come on top of that. Would take those and then say what is my objective function, and say go for typical descent gradient optimization. And this would in fact be iterative and then decide or come up with new proposals for new samples to be simulated. And this is, but again, this responsibility of, say, the strategy of resampling and also the acquisition function, so which actually proposes a new sample. These are different roles. I mean, maybe we include them in farm, but I'm always a friend of modularization, so not squeezing responsibilities into the very same package that don't say solve the same challenge or have distinct responsibilities. But yeah, it lays ground.
In my head, you probably would have want to build some piece of software that does the optimization and uses farn in the background.
Exactly.
All right. Thank you very much, Claas.
Thank you.